Welcome to this coding solution walkthrough. In this session, we'll be tackling the problem number 404, titled Sum of Left Leaves. This is an interesting problem that involves exploring binary trees and applying efficient traversal techniques. Let's dive in and get started. In this problem, we are asked to calculate the sum of all left leaves in a binary tree. Now, let's break this down. A leaf is a node in the tree that does not have any children, meaning it is at the very end of a branch. A left leaf, specifically, is a leaf node that is the left child of its parent. The input to the problem is the root node of the binary tree, and the output we need to produce is an integer representing the sum of the values of all these left leaves. To better understand this, let's consider some examples. Take this example where the binary tree is structured with the root node as 3. The left child of 3 is 9, and the right child is 20. Node 20 has two children, 15 on the left and 7 on the right. Here, the leaf nodes are 9, 15, and 7. Out of these, the left leaves are 9 and 15, as both are left children of their respective parents. Their values, 9 and 15, add up to 24, which is the result. Now, consider a simpler example with a single node, 1. Since there are no children, there are no left leaves, and the output is 0. This demonstrates how the sum depends on the presence of left leaves in the tree. In another example, we have a tree where the root node is 1, and its left child is 2. Here, the only leaf node is 2, and it is also a left leaf because it is the left child of its parent, 1. Therefore, the sum of left leaves in this case is simply 2. Beyond these examples, the problem also comes with certain constraints. The number of nodes in the tree can go up to 10,000, and the values of the nodes can range between -10,000 and 10,000. We also need to consider edge cases, such as trees with no left leaves or trees with left children that are not leaves. By keeping these constraints and edge cases in mind, we can ensure our solution handles all possible scenarios correctly. To solve the problem of summing all left leaves in a binary tree, there are three main approaches to consider, starting with the recursive depth-first search, or DFS. This method uses recursion to naturally traverse the tree. At each node, we check if its left child is a leaf, and if so, we add its value to our running sum. We then recursively process both the left and right subtrees. This approach is intuitive because recursion mimics the hierarchical structure of a binary tree, allowing us to break the problem into smaller, manageable subproblems. In terms of efficiency, it has a time complexity of O(n), where n is the number of nodes in the tree, since each node is visited exactly once. The space complexity is O(h), where h is the tree's height, as the recursive call stack will hold up to h nodes at any given time. This method is clean and easy to implement, but it does have a drawback. For very deep trees, the recursion depth could lead to stack overflow. Another option is iterative DFS, which eliminates recursion by using an explicit stack to simulate the traversal process. Here, nodes are pushed onto the stack, and we check for left leaves as we pop them off. Both left and right children are added to the stack for further exploration. This approach avoids the risk of stack overflow, making it safer for deep trees, though it can be slightly more verbose in implementation. In terms of complexity, the iterative DFS approach is also O(n) in time and O(h) in space, as the stack will store nodes proportional to the height of the tree. Its main advantage lies in avoiding recursion, which can be a critical factor for deeply nested trees. However, the code tends to be less elegant than the recursive solution. Now, the third method we considered is breadth-first search, or BFS, which uses a queue to perform a level-order traversal of the tree. For each dequeued node, we check for left leaves while unqueuing any existing left or right children. BFS processes nodes level by level, which is particularly useful when the order of traversal matters, though it isn't strictly required for this problem. The time complexity here is also O(n), since every node is visited once. The space complexity, however, is O(w), where W represents the maximum width of the tree, or the largest number of nodes at any level. This can require significantly more memory compared to DFS, especially for wide trees. BFS is straightforward to implement and avoids recursion entirely, but the overhead of maintaining a potentially large queue is a notable downside for this method. Overall, these three approaches each offer unique advantages and trade-offs. For this problem, we chose the recursive DFS approach as the most suitable solution. This decision was based on a few key factors. First, the simplicity and readability of recursive DFS make it a natural fit for a problem like this. The recursive structure directly reflects the hierarchical nature of binary trees, making the code easier to write, understand, and debug. Second, it is efficient, with a time complexity of O(n), due to visiting each node only once, and a space complexity of O(h), which is typically acceptable for most trees except in cases of extreme depth and imbalance. Third, recursive DFS aligns perfectly with the problem's requirements to identify in some left leaves, allowing us to focus on the core logic without the added complexity of managing explicit stacks or queues. Comparing this approach to iterative DFS, we find that while the iterative method avoids recursion, it is more verbose and less intuitive. On the other hand, DFS requires additional memory for the queue, which can be a significant drawback for wide trees. In contrast, recursive DFS strikes the right balance between simplicity, efficiency, and memory usage, making it the ideal choice for this problem. In this problem, we're tasked with calculating the sum of all left leaves in a binary tree. A left leaf is any node that is the left child of its parent and has no children of its own, meaning both its left and right pointers are null. To solve this, we'll use a recursive depth-first search, or DFS, which is particularly well suited for tree traversal. The algorithm begins with a base case. If the current node is null, we simply return 0. This ensures that we handle empty subtrees cleanly without performing unnecessary computations. Next, for any given node, we check if its left child is a leaf. If it is, we add its value to the sum. If the left child isn't a leaf, we continue the recursion to explore deeper into the left subtree. Finally, we also recursively process the right subtree for the current node, as it may have its own left leaves. The combination of these steps ensures that we comprehensively traverse the entire tree while focusing specifically on the left leaves. After processing the left and right subtrees, we combine the results to compute the total sum for the current node. This sum consists of three components: the value of the left leaf, if one exists, the sum of left leaves in the left subtree, and the sum of left leaves in the right subtree. Once we've accumulated this total, we return it to the parent call. Recursion is a natural choice for tree traversal because it mirrors the hierarchical structure of the tree itself. By using recursive DFS, we can handle one node at a time while seamlessly exploring its subtrees. Checking the left child first is critical because the problem specifically focuses on left leaves. By addressing this case upfront, we avoid unnecessary computations and directly address the problem's requirements. It's also important to consider edge cases, such as when the tree is empty, when it contains only a single node, or when all left children are internal nodes. These scenarios ensure our algorithm is robust and doesn't fail under special conditions. For example, in the case of an empty tree where the root is null, the sum of left leaves should naturally be 0. Similarly, in a tree with just one node, there are no leaves at all, so the sum also remains 0. When all the left children in the tree are internal nodes, the algorithm ensures that only the values of true left leaves are included, excluding non-leaf nodes. Structurally, the binary tree is the primary data structure, where each node has a value, and pointers to its left and right children. The recursion itself uses the call stack to keep track of nodes during traversal, so no additional data structures are needed. Analyzing the algorithm's efficiency, the time complexity is O(n), as each node is visited exactly once. The space complexity is determined by the recursion stack, which depends on the tree's height. For a balanced tree, this is O log n, while for a skewed tree, it's O(n). To see the algorithm in action, let's walk through an example. Consider a binary tree where the root is 5, with left and right children 3 and 8 respectively. Node 3 has its own children, 1 and 4, and node 8 has a right child, 9. We start at the root, node 5. First, we look at the left child, node 3. Since node 3 is not a leaf, we recursively explore it further. Then we check the right child, node 8, which is also not a leaf, so we recurse on it as well. At node 3, we check its left child, node 1. This node is a leaf, as it has no children, so we add its value, 1, to the sum. Next, we look at the right child of node 3, which is node 4. Node 4 is not a leaf, so we continue the traversal. Back at node 8, we check its left child, which is null and can be skipped. The right child of node 8 is node 9, which is not a leaf, so we recurse on it. Once all nodes have been processed, we combine the sums. In this case, the only left leaf is node 1, so the total sum is 1. This step-by-step traversal ensures that we capture all left leaves while ignoring irrelevant nodes. The corresponding Python implementation begins with a function that accepts the root of the tree and initializes the sum to 0. If the root's left child is a leaf, we add its value to the sum. Next, we recursively calculate the sum of left leaves in the left and right subtrees by invoking the function on the left and right children. The results from these recursive calls are added to the current sum, and the accumulated total is returned. This approach is efficient because it avoids redundant checks and focuses only on the nodes relevant to the problem. By leveraging recursion and the call stack, we eliminate the need for additional data structures, keeping the implementation clean and straightforward. Additionally, checking for left leaves directly ensures that we handle the problem efficiently without unnecessary overhead. With this implementation, we achieve an optimal balance of clarity, simplicity, and performance, making it a reliable solution for computing the sum of left leaves in any binary tree. This Python solution for LeetCode problem number 404, sum of left leaves, uses a recursive depth-first traversal to compute the sum of all left leaves in a binary tree efficiently. Let's break it down step by step. First, the treeNode class is defined to represent nodes in the binary tree. Each node contains a value, val, and pointers to its left and right children. The solution class encapsulates the main logic for solving the problem. The sum of left leaves function begins by defining a helper function called is_leaf. This function determines whether a given node is a leaf by checking if the node exists and has no children, left and right or both none. This helper function is critical for identifying left leaves during traversal. The base case checks if the root is none, meaning the tree is empty. In this case, the function returns 0, as there are no nodes to process. Next, a total variable is initialized to 0. This variable accumulates the sum of all left leaf values as the tree is traversed. The function checks if the current node's left child exists and is a leaf, using the is_leaf function. If true, the left child's value is added to total. The function then recursively calculates the sum of left leaves for the left and right subtrees by calling sum of left leaves on root.left and root.right, respectively. These recursive calls ensure that all nodes in the tree are processed, and any left leaves encountered are included in the sum. Finally, the total is returned, representing the sum of all left leaves in the binary tree. This approach efficiently traverses the entire tree and ensures that only left leaves contribute to the sum. Overall, this implementation is concise, handles edge cases, such as empty trees, and adheres to the problem's constraints. The algorithm runs in O(n) time because each node is visited exactly once during the traversal, where n is the number of nodes in the binary tree. Here, we're starting with the Java implementation for the problem. We first define the structure of our binary tree node using a static inner class named treeNode. Each treeNode object has an integer value, along with references to its left and right children. Two constructors are provided, one initializes the node with just a value, and the other allows us to initialize it with a value as well as its left and right child nodes. Below this, we define the sum of left leaves method, which is responsible for calculating the sum of all left leaf nodes in the tree. The first step in this method is a base case to check if the root is null. If it is, we simply return 0, as there are no nodes to process. We then initialize a variable called total to keep track of the cumulative sum of left leaf nodes as we traverse the tree. Now, we check whether the current node's left child exists and if it is a leaf node. A node is considered a leaf if it has no left or right children. If these conditions are met, we add the value of the left child to our total variable. After this, we recursively call the sum of left leaves method for both the left and right subtrees of the current node. These recursive calls ensure that we explore the entire tree and account for all left leaves. Finally, we return the total sum. This approach ensures that we traverse the tree efficiently while correctly identifying and summing up all the left leaf nodes. Let's look at the first example, which involves a small tree. The root node has a value of 3, and it has two children, a left child with a value of 9 and a right child with a value of 20. We start by initializing a variable, total, to 0. Next, we check the left child, which is the node with a value of 9. Using the is_leaf helper function, we determine that this node is a leaf because it has no children. Since it's a left leaf, we add its value to total, updating it to 9. Then, we recursively call the sum of left leaves function on node 9. However, because node 9 is a leaf, the recursion immediately returns 0. Moving to the right child, which is the node with a value of 20, we initialize another total variable to 0. We then check its left child, the node with a value of 15. Again, the is_leaf function confirms that node 15 is a leaf because it has no children. Since node 15 is a left leaf, we add its value to total, updating it to 15. Next, we recursively call sum of left leaves on both the left and right children of node 15, but since they are none, both calls return 0. Now, we proceed to the right child of node 20, which is the node with a value of 7. Node 7 is not a left leaf, so we don't add its value to total. The recursion for this node also returns 0. Adding up the results, the total for node 20's subtree is 15. To calculate the total for the entire tree, we sum up the results from the root's left and right subtrees. This gives us total equals 9 plus 15 equals 24. Therefore, the output for this example is 24. Next, we'll examine a case where the tree has no left leaves. In the second example, the tree is structured such that it has only right children. The root node has a value of 1, with a right child of 2, which in turn has a right child of 3. We start at the root and initialize total to 0. Since the root has no left child, there's no value to add to total. We then recursively call sum of left leaves on the root's right child, which is the node with a value of 2. At this node, we again initialize total to 0. Similar to the root, node 2 has no left child, so we don't add any value to total. Next, we recursively call sum of left leaves on node 2's right child, which is the node with a value of 3. At node 3, we initialize total to 0 once more. Node 3 also has no left child, so no value is added. Then, we recursively call sum of left leaves on both the left and right children of node 3, both of which are none, so the recursion returns 0 for both calls. With the recursion complete for node 3, the total for its subtree is 0. Similarly, the total for node 2's subtree is 0. Finally, the total for the entire tree is also 0, as there are no left leaves anywhere in this tree. This gives us an output of 0. For the final example, consider a tree with only a single node. The root node has a value of 5, and it has no left or right children. We start by initializing total to 0. Since the root has no left child, there's no value to add to total. We then recursively call sum of left leaves on both the left and right children of the root, but since both are none, these calls return 0. As a result, the total for the entire tree is 0, and the output is 0. This demonstrates how the function handles an edge case with the smallest possible tree. To analyze the time complexity of the solution to the sum of left leaves problem, we start by looking at the recursive traversal of the binary tree. The function sum of left leaves visits each node exactly once as it recursively explores both the left and right subtrees. This ensures that every node in the tree is processed, making the traversal inherently O(n), where n represents the total number of nodes in the tree. Additionally, there's the helper function is_leaf, which checks if a node is a leaf. This function operates in constant time, O(1), as it performs only a few conditional checks. Since this helper function is called at most once per node, its contribution to the overall time complexity is proportional to the number of nodes. Combining these observations, the time complexity for the entire solution is O(n), driven by the single traversal of all the nodes in the tree. The space complexity of this solution is primarily influenced by the recursive call stack. In a recursive algorithm, the depth of the stack corresponds to the height of the binary tree. In the worst-case scenario, where the tree is completely unbalanced and resembles a linked list, the recursion depth equals the total number of nodes, n, leading to a space complexity of O(n). Conversely, in the best-case scenario of a perfectly balanced binary tree, the recursion depth is proportional to the logarithm of the number of nodes, resulting in a space complexity of O log n. It's also worth noting that no additional data structures are used, so the auxiliary space remains constant at O(1). Therefore, the overall space complexity is determined by the tree's height, which can range from O log n to O n, depending on the tree's structure. When we compare this solution to a potential brute force approach, the optimizations become clear. A naive method might involve traversing the tree multiple times, such as once to collect all left leaves and again to sum their values. This would lead to a time complexity of O n squared, in the worst case for unbalanced trees. The current solution, however, combines the identification and summation of left leaves into a single traversal, achieving a far more efficient O n time complexity. In terms of optimality, this solution is the best possible for a problem requiring every node in the tree to be visited. No further improvements are feasible without imposing additional constraints. Considering different scenarios, in the best case of a perfectly balanced tree, the time complexity remains O n, while space complexity is O log n. For the worst case of a completely unbalanced tree, both time and space complexity are O n. In general, for an average binary tree, the time remains O n, and the space complexity typically aligns with the height, often closer to O log n, for reasonably balanced trees. To mathematically confirm the big O analysis, we note that each node in the binary tree is visited exactly once during the traversal. At each node, constant time operations are performed, such as checking whether the node is a leaf, summing its value if it's a left leaf, and making recursive calls. This results in a total time complexity of O(1) work per node, multiplied by n nodes, giving O(n) overall. For space complexity, the key factor is the recursion depth, which reflects the height of the binary tree. In the worst case, where the tree is unbalanced, the height equals the number of nodes, n, leading to O(n) space usage. In the best case of a balanced tree, the height is logarithmic, or O log n. Thus, the time complexity of O(n) and the space complexity of O(h) are mathematically validated, where h represents the tree height. When solving this problem, there are a few common mistakes to watch out for. First, misidentifying left leaves is a frequent error. It's important to remember that a left node must also be a leaf, meaning both its left and right pointers should be null. If it has its own subtree, it doesn't qualify as a leaf and shouldn't be included in the sum. Another issue is with the base case in recursive solutions. If you don't properly handle null nodes by returning 0, you might run into unnecessary errors. Beginners sometimes overcomplicate the logic by adding redundant checks or splitting the process into multiple traversals when it can be streamlined into a single step. Additionally, edge cases like an empty tree or a tree with just one node are easy to overlook but can cause runtime errors. Finally, while recursion is a natural fit for this problem, don't ignore iterative solutions. Interviewers might ask for an iterative approach, so being comfortable with stack-based implementations will give you more flexibility. This problem is a great test of your ability to systematically traverse a tree while applying specific conditions. The key challenge is to correctly identify and sum left leaves, and overthinking the problem can sometimes lead to unnecessary complexity. Be ready to discuss the trade-offs between recursion and iteration. Recursion often makes the code cleaner but can lead to a stack overflow if the tree is very deep. Iterative solutions avoid this issue by handling the stack manually, but the implementation can be more verbose. Interviewers might also build on this problem with follow-up questions, such as asking for sums of right leaves or nodes at a certain depth. These variations require you to generalize your approach effectively. Recognizing this problem as part of the broader tree traversal with conditional aggregation pattern can help you apply similar strategies to other problems. There are several related problems that share similar traversal mechanics or aggregation logic. For instance, sum of root to leaf binary numbers involves traversing the tree, but instead of summing specific nodes, you're aggregating binary values along the paths. Another example is path sum, which focuses on summing up the values along specific paths rather than individual nodes. Binary tree paths is another variation that requires generating all paths from the root to the leaves, which involves a different way of handling and storing data during traversal. Lastly, problems like count complete tree nodes introduce optimization techniques for tree traversal, providing opportunities to practice efficient algorithms. Understanding these related problems can give you a broader perspective on tree traversal patterns. There are multiple approaches to solving this problem, each with its own trade-offs. Recursive DFS is the most intuitive for many, as it mirrors the natural structure of the tree. However, it can lead to stack overflow in the case of highly unbalanced trees. Its time complexity is O, n, where n is the number of nodes, and its space complexity is O, h, where h is the height of the tree due to the recursive stack. Iterative DFS, which uses an explicit stack, avoids recursion risks and gives you better control over memory usage. However, it can be more verbose and error-prone during implementation. BFS, on the other hand, traverses the tree level by level. While it's less natural for this specific problem, it can be useful when additional conditions, such as level-based calculations, are introduced. BFS has a time complexity of O, n, and a space complexity of O, w, where w is the maximum width of the tree. Understanding these trade-offs will help you choose the best approach for different scenarios. To wrap up, this problem highlights the importance of mastering both recursive and iterative tree traversal techniques. Make sure to practice handling edge cases, such as empty trees or trees with just one node, to ensure your solutions are robust. Recognizing the underlying pattern of a tree traversal with conditional aggregation is key to solving not just this problem but a range of similar challenges efficiently. With a solid understanding of these concepts, you'll be well prepared to tackle both variations of this problem and related ones in interviews. Thanks for sticking around. We've summarized the problem, solution, and key insights. Remember, mastering tree traversal techniques is valuable for many coding scenarios. We hope this was helpful. Be sure to like and subscribe for more content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!